One of the benefits of coming here in person is people are always being hired from CppCon. Companies are here looking for the best in the world and good talent. So whether it's career or networking or just building up your technical skills, most of those you won't get from just the video, but that you can get from being here.
Hi, my name's Jubin. I'm going to be talking about that title, but I think that was a good one to get the presentation accepted. I think if you want to refer to this talk, you can use this one. I also asked my coding agent for a bunch of suggestions. I think there's one which is called Dark Code, Bright Agents, which was a good runner-up topic to it as well. So we are a session after lunch, so people are going to keep coming in, which is totally great. We have a mic here. The talk has about 5 segments. So we have I encourage people to ask questions after the end of each segment, and please come to the mic, which will be great for the video to capture it as well. So just about me, I'm Jubin. I'm an engineer at Facebook, on Facebook app. It's at the Blue app. And I tech lead the Meta AI on Facebook, which is basically our AI chatbot and AI assistant that helps people with a bunch of different tasks on Facebook app, things like getting more context about posts, trying to verify things like misinformation, also doing things like helping people write and compose posts or compose comments, a bunch of different AI use cases. I think the big niche that we have found is the information-seeking use case. Facebook has been a great place for people to go for social connection and for entertainment. For info-seeking, we've had lots of products in the past, but this is the one that seems to hit the spot. I also lead Facebook's AI native program, which is effectively our focus on doing all our activities of product development, coding, testing, deploying data analysis using AI tools first. So this is a group of about 25 engineers who are all like in pods of 3 using AI tooling for all of the things that they do. So yeah, just to tell you a little bit about my project, it's the project I lead has about a billion plus monthly actives, and it's at kind of Facebook scale. We use reasoning models and agentic models for this. We are close to about finding product market fit on that feature as well. So no talk should go without a meme. This is a meme which is now actually 3 years old on Reddit, which is AI just helps me code faster, but my debugging time goes up n times. This meme seems to have aged a lot. I don't know how many people's experiences we still struggle to get things done using AI agents, and it takes much, much longer to actually finish the task. And this is another meme, so every talk should have a second meme as well, which is that there's always the complexity of doing things like dealing with test frameworks and dealing with coding standards and dealing with ever-moving platforms and so on, which we always had, which is the top panel. But now everybody else thinks, whoever's not writing code thinks that you just prompt the AI and the code gets generated and you can deploy it to production. Well, now we have to deal with AI patterns and prompt engineering and context engineering and so on, and we still have to deal with all the other stuff as well. So if you're feeling the first or the second meme, I don't know if you identify yourself in any of those memes, I'm hoping that this talk will take you in a somewhat a little bit better place than where this is. So what we should be able to take away from this is understand a little bit more deeply how AI agents actually work. What are the key kind of architectural pieces of them, and this will help us get more value out of using them for data analysis, for writing code, for refactoring, for testing, deployment, all that kind of good stuff. And then the ever impending code quality crisis that many of us at large organizations have to deal with, and with the advent of vibe coding and AI agents, how that's becoming challenging, but how perhaps the same AI agents can help us with both the offense and the defense on upholding quality standards in code. So these are the kind of 3 takeaways from the talk. Just to keep it interesting, because they told me it's after lunch, so I have a cyberpunk kind of format here. It's like going chapter by chapter. In a galaxy not far, far away, which is like challenges of scale and need for focus on code quality. So I'm just going to describe an abstract organization, hundreds of millions of lines of code, 10,000 developers, 10,000 plus commits a day, 15 years of code base, backend code, ML code, mobile, AI, product infrastructure. No prizes for guessing which one this is. We actually have a reference at the bottom on the paper that talks about what we're doing. So this is Meta's situation. But I'm sure many of you find yourself in something like this. For this audience, it's not a new thing when I speak about code quality. And just to be clear, I'm not talking about perhaps just focusing on bugs or focusing on product craft. I'm talking about coding standards and code that's maintainable, that's easy to work with, that complies with, but the compiler doesn't throw a bunch of warnings every time you have to compile your code, all that kind of good stuff. Almost from the time that we've had large enough code bases, we've been talking about the challenges of upholding code quality. And this triangle is one that's often thrown at us, which is that, hey, you can have 2 of these, but not the third one. So as long as you're willing to give up a little bit on the third one, you can get the other 2. So if you want to get something done with a limited amount of effort or limited team size, and you need it done by the next N months or N weeks, you have to make some compromises on the scope or the quality. And then you can pivot this triangle around and you can pick and choose 2 of these, but not the other. I think this works okay for the very short term for that particular project perhaps, but in the long run, almost all of these things constrain you on the other dimensions. If you have poor quality on your code base, if you racked up a lot of technical debt, well, guess what? Your cost and your time to market are going to be impacted, and you accumulate this over a period of time. I tried to prompt AI to change this triangle into a different shape to communicate that idea, but the AI is not there yet, or maybe my prompting standards are not there yet. I also borrow from another study we've done at Meta on looking at different metrics around risk, so things around outages, and looking at time to market or like product development velocity. And I think this was a code I've just picked from there, which is that there's an inverse relationship between the delivery of software changes and the outages you will see. So if you accelerate delivery of code changes, you are going to suffer on the side of outages. I think that's kind of well understood. I think there's a line here which is talking about the simplest way to solve this problem, to have no outages, is to never change the code. I think that can only happen if we're not delivering value for the business. We're working on code bases that do have to evolve. So to make this kind of more data-oriented, there's another paper from the same kind of data science team that we have in Meta that talks about the correlation. I don't know if the people at the back can see it. It's a little bit maybe slightly unclear, but I'm just going to pick a couple of ways of measuring the upkeep in the code base. So the amount of dead code that exists in the code and the cyclometric complexity of the code, and there's a bunch of different CCN metrics that are used here. What we find is that when we have some dead code or if the complexity is beyond a certain threshold, if it's highly complex, the likelihood of it to cause a SEV, which is like Meta's way of calling outages, severity outages, you will see the rate of a file being part of an outage goes down from 76% down to 24% once you remove all the dead code out of it. And once you reduce the code complexity below a certain threshold, which they've defined and talk about in the paper if you're interested, you're bringing it down from 80% down to 20%. So likelihood of a file being included in the outage goes down dramatically. I think we kind of intuitively already know that, but I think having the data in front of us at like looking at tens of thousands of diffs and hundreds of outages really helps back this up. So I'm not going to spend more time on proving this. Just one last more data point around dead code removal, reducing cyclometric complexity, decomposing large kind of classes down, and platformization, which is just basically keeping up with the latest standards in the programming language. All of these things improve the diff authoring time, which is just measuring how long an engineer takes to on the IDE to go from ideation, from starting a code change all the way to finishing the code change. All of these things, they found enough statistical significance to be able to tell you that improving the quality of the code will actually help you get things out the door. So I think for this audience, if you ever had to argue with somebody to like prioritize code quality, you have the hard data. You can go back and refer to it here. And I think just to quickly talk about like why we get here, we often have to prioritize time to market. That's fine. We also often have newer engineers joining the team, churn on the team, people move on to other things. There's a general half-life of an engineer in the industry on a code base. But also often if you haven't made efforts to defend things like test coverage or complexity of the code base, we are going to end up in this situation. So yes, and then features go out of use, but the code still remains. That code still gets maintenance. The dead code still gets upgraded often. It's actually more work for keeping the code alive, which is already kind of past its value. So this is like section 1 was like kind of straightforward. I don't know if anybody had any questions. This is the time to ask me, or we can keep moving. This is just the warm-up of the talk of why code quality matters and like why the data is like very clear about this. Yeah, if no questions, I can keep moving. So all that's great. Now this is the next thing. So we are in kind of an unprecedented time in terms of the amount of code being generated using AI tooling. So if you have headaches about code complexity and code quality 3 years ago, well, welcome to 2025, the year of the rise of the vibe coder. So there is a new canon in programming, the Karpathy canon. We've had prior canons, right? You can go back to Knuth's one in 92 about literate programming and egoless programming before that. But what's unique is the Karpathy canon is like super long, 185 words long. It's basically this tweet that goes out the beginning of the year. There's a rise of a new thing called as vibe coding. I'm not going to read through the whole thing. Let me just pick the juicy highlights here. I asked for the dumbest things like decrease the padding of the sidebar by half because I'm too lazy and I accept all the changes. The code grows beyond my usual comprehension. Sometimes the LLMs can't fix the bug. I still see stuff, say stuff, run stuff, and copy stuff, and it mostly works. It mostly works. And because it mostly works, it mostly makes it to production, and it mostly is used by most people, most of the time, until it doesn't. And then 3 years ago, there's the talk about the hottest new programming language, which guess what is not C++, it's English. But what could go wrong? When I was trying to look into this topic, I found like a lot of like papers coming out about this, where folks have come up with taxonomies of different kinds of bugs and problems that the LLM models of that particular time have been causing. There's like functional bugs, runtime bugs, etc. I think the data is a bit difficult to read, but the point of the slide is that the section in the red, which is all your functional bugs. The rows are basically types of bug, and the columns are the types of other different models. I think there's a concentration of functional bugs. And these are very hard to find at the time of coding, especially if you have a laissez-faire attitude, which is like, if it works, I'm going to move forward. So, and there's like paper after paper talking about like scientifically proving this particular concept. So what are people mostly using vibe coding for? Mostly for 0 to 1 prototypes, for getting a feel for the problem, for iterative development, for going back and forth, trying to like come up with a basic design for new things. But people are also using it to update existing code bases, for refactoring them, etc. And then there's a different paradigm from vibe coding, which is AI agents. I think it's important to like figure out the difference between these two. So vibe coding is when you're iteratively working with an agent or with its predecessor, which is the coding LLM, trying to kind of construct a somewhat working system for yourself to get a feel for what your project should look like. AI agents, on the other hand, let's try to define these so that we can reason about them going forward. So there are like 4 characteristic properties. There's not enough unanimity on this, but for today, let's try to like agree on these 4, and then we can evaluate as we go forward on like how different approaches fit with these. So you have autonomy. So the agent needs to be able to take decisions and actions on its own for the most part, and only when it gets really stuck or it's super ambiguous, should it escalate and ask you more questions, ask a human or ask another agent for questions. The process needs to be interactive, so the agent needs to have access to tools and memory and other agents, so it needs to be able to interact with the rest of the world. Its predecessor, the coding LLM, did not strictly have access to all of these things outside its control, outside its world. Third principle is like iterative. So it needs to reflect on its own work. So whatever works it's creating, it needs to be able to reason about whether it did a good job or where it's lacking, and then how can it improve. And also look at feedback from the results it's getting from the tools and other agents and things outside its immediate control. And it needs to be goal-oriented. So if we agree on these 4 principles of how we define an AI agent, we can definitely say that heuristic approaches for writing code or traditional ML models for writing code, or even a one-shot LLM where you describe the problem and you give one example, does not fit these 4 principles quite right. So an example of something that an AI agent is able to do, but the previous iteration of coding LLMs were not able to do, is things like, an example is implement a REST API endpoint that returns top 10 most frequently accessed URLs from a web server log, and then include unit tests and include documentation. So this task requires like working on multiple files across multiple components, and you have to implement a bunch of different technology here, writing tests and writing documentation. We'll go into this particular example in a little bit more detail. But let's say we agree to this. We also hear from all of big tech CEOs talking about, hey, more than 30% of our code is now AI generated, and it's giving us like 10% gains in productivity. I could not find a public code from Meta, so I haven't included it, but I think you can assume it's kind of in the same vein. So 30% of the code, and this number keeps rising, and there are claims that it'll be 100% within like the next N years. Take your pick on how long N is. But given that the percentage of code characters being generated by agents continues to grow, we are going to continue to have that challenge on code quality unless we kind of ramp up our game on dealing with it. So I'm going to talk about a couple of small points, and then we'll go to the next section. One is about how we should look at code quality in this world of vibe coding and AI agents who are writing product features. If you look at the second section around associated source code files, again, what we see is that AI agents perform better if code is less complex. So this is the flip side of the earlier discussion I was talking about, which is that if code quality is better, then the outages are less and the velocity is higher. This is a related piece where if your code is less complex, although it's doing the same function, the same code base before complexity, with high complexity, or the same code base after it's been refactored to have low complexity, the likelihood of an agent to successfully complete a task on it increases quite dramatically, and that's what this study is showing, which is that based on lines of code or based on CCN, as you start to make the code base simpler, your likelihood of the AI agent finishing its task improves dramatically. So even if you're very much in the camp of like, AI agents are here to stay, they're the best thing ever, you want to improve the code quality of your code base because they will get much more out of your agents, and you will save both wall clock time and also the likelihood of a task finishing. And because the likelihood of a task finishing improves, your token usage on tasks that never work out also improves. So it is also a cost saving. So it's both time to market saving, cost saving, and just like likelihood of it not having fewer bugs improves. So with that said, we will want to focus on two things. The things I want you to take away from the talk is, how do I leverage agents for my feature development or getting my projects out the door? And secondly, how do I use AI agents for improving code quality? I think this is the end of this section. Any questions so far before we go into the meat of the talk? Cool. So now the next three sections are gonna be, one is gonna be about like a deeper dive about how agents actually work, the internals of these things. Chapter 4 is about using AI agents to speed up your product development and being more successful with getting your tasks from 0 to 1. And then finally talking about a few different approaches on improving code quality, reliability, testing, test coverage using AI agents. So the anatomy of an agent. This slide's basically just showing you the evolution of a few different key innovations that help AI agents become AI agents from what they used to be, which was mostly coding LLMs. Most of us, as you can see, just picks up in 2023 and onwards. So we are probably in year 3 of the era of the agent, if you will, or at least AI agent for coding. I think key innovations that we will talk about is like if you look at the extreme left of the chart, it's talking about self-planning, self-refining, debugging, editing, etc. So I think there are a few core concepts that make an agent an agent. The ability to plan, the ability to reason about and reflect on its own work, and the ability to hold context down as memory and pass that and communicate with the other agents, where I'll also include tool calling, which is the agent's ability to do things in the real world. Things like executing code or compiling, looking up databases, all that kind of good stuff. So a lot of these are like seminal works or like systems that people build, which are like iteratively showing how different techniques help you do any of these tasks around planning, reflection, tool calling. So yeah, so we get into just how a very, very, very high level overview of how a single agent code generation would work. So if you focus on the yellow section, we are asking the agent to create a quicksort algorithm in Python. The agent has to do a few things, has access to a few capabilities: planning, tool calling, and reflection. And the output would be hopefully a working algorithm, hopefully with test cases, and reasonable amount of documentation, and hopefully it works most of the time, or at least works hopefully all of the time for a task as simple as that. So the way the planning and reasoning would work is you have the query or the prompt as an input to the agent. The agent comes up with a plan. Here what we found is that actually forcing agents to articulate their plan, which is the steps of what they would do to achieve the task, is an important step in its capability. So getting agents to become very good at taking a prompt and then creating a very, very clearly defined plan, ideally in natural language, but at least in a format that is very well clearly understood, is the first key step. So you basically, in the blue section, what you're doing is taking the query and you're creating a plan. Then the next stage is, now that the plan is created, that agent is going to start executing on that plan. To be able to execute on the plan, it will need to call out to some external tools. So the quicksort example is perhaps trivial, but in many cases you will have to, actually maybe the tool calls here are also necessary. You need to compile it. You might need to find where this file needs to sit in the rest of the directory structure. You might want to do static code analysis, etc. So there are tool calls to be made for that. And then kind of related concept is around retrieval augmented generation, which is where you are able to make out, get more context, more information on how to do the task, or get more data that helps you get the task done. So you can look at a RAG as a way to get more data or more context to help achieve the task at hand. And tool calling is to do things and actions in the world. Although tool calling also produces results, which in a way are also giving you data back. So that's the stage about tool calling. And then finally, you have reflection and self-improvement, which is once the first iteration is done, the agent needs to be able to evaluate that, evaluate its own work. So it could do things like making sure, finding bugs in the code, making sure it's using things like memory and other resources well enough. Is the code well structured? All that kind of good stuff. So these are the basic activities of a single agent code generation. Multi-agents just kind of scale this up. Multi-agents can then help you specialize where each agent is providing a specialized capability. In this case, if you go back to the REST API example, now here you might have agents to want to create some kind of workflow. So there are a bunch of stages that need to be done. The moment you have multiple agents, now they need to be able to share context, and they need to be able to collaborate on the work together. So let's look at this again with the same kind of color scheme. There are a bunch of different paradigms or patterns that people have proposed of how to organize agents. And we will spend a little bit of time talking about this. So I'm not going to spend too much time looking at these, but these are patterns of like how these agents should be set up. And the next part is like around how they should share context. And finally, how should they collaborate? So compared to single generation, we take the single generation example. And then when we scale up, we have this added complexity of setting up a workflow, context sharing, and collaborating. How is all of this different than coding LLMs? So coding LLMs are actually LLMs that were, or they are still LLMs that are trained on open source code libraries and programming documentation. Basically, their job is to be able to write code in one or more languages very well. Their task is not to do all the other things which we are describing here, which is to call out to file systems and compile the code, all that kind of other things. So the coding LLMs can still be a fundamental unit in how code is written. So examples here could be CodeLlama or Codex, DeepSeek Coder. These are the examples of code LLMs. Tech that was very, very hot before agents start to pick up in 2023, although still you can get a lot of value out of having a coding LLM as a component in your agentic architecture. So yeah, we just spoke about the differences. I'm just bringing this slide up again because I wanted to show you the example. So we are going to try to look at the example of implementing a REST API endpoint that returns the top 10 most frequently accessed URLs. And then we want to write tests and documentation. So how is this going to play out in an agentic workflow? So the first step is to understand the prompt. This is just the stuff that LLMs have been good at, which is to take natural language and kind of translate that into their internal context tokens. From there, they need to articulate a plan, which you can force them to kind of show you via like sharing that out, or you can hold that internally in the LLM. But the planning is a key step. Models are trained to create plans in a generic fashion. We'll talk about that very briefly. So you can have a generic planner, which can plan for any kind of activity, regardless of whether it's coding or it's some other type of activity for any real-world task. Or you can have a coding or a software engineering specific planning model there. Next, it needs to write a bunch of code, which includes traversing the file system, finding a bunch of files, refactoring them to introduce the particular feature, and do things like compiling that, testing that, all that kind of good stuff. So step 4 is writing the tests, building and executing the code, and then finally documenting it. So you have multiple steps to be done, and at each step, you want to be able to verify the work that's being done, and if many of these steps will actually fail, and when they fail, the model needs to be able to consume the failures and then be able to adapt its plan. So this is the key steps that an AI agent is taking. Many of these steps require tool calls, and many of them require reflection, unlike what one-shot coding LLMs were doing for us in the past. So I spoke about the reasoning model. So reasoning models are generic reasoning LLMs. They can do things like code generation, task planning, debugging, but they can also do other real-world activities, and some of these are like GPT-5 or the latest kind of DeepSeek and Gemini models, which are in the generic reasoning space. They are also able to generate kind of syntactically correct and meaningful code and answer questions for you and engage in multi-turn conversations, all that good stuff. And what we are now seeing is that certain reasoning models, like the latest stuff from Grok and from Anthropic's Cloud Opus, we start to see that they are also being optimized for coding tasks. So the generic reasoning model is actually starting to get to par or outperform coding LLMs as well. So depending on the language and the context, you might see, if you do evals, you might see value in the coding specific LLM for your coding task, or at least the subtask for coding, or the generic model is actually good enough in many cases, is what we are starting to see. It's worth also talking very quickly on the evolution of the prompt engineering and reasoning strategies here. So coming from the coding LLMs, we moved to the chain of thought prompting. Chain of thought was basically explicitly asking the model to be explicitly telling you its reasoning steps and using that to improve its kind of problem-solving abilities. That was chain of thought prompting. We moved from that to React. React is basically reasoning and acting. So here the key delta between that and chain of thought is the ability to be able to take concrete actions and reason about the output of those actions. So now you're creating a plan and you're acting on the plan by hitting an MCP or like a tool server, and the tool server is doing a bunch of tasks for you, and then the results come back for it, and you can reason about it. And finally, we move on to other paradigms where we do things like scratchpad prompting, where the LLM needs to be able to like manage this context in its memory, and you can start to inspect its plan in memory. So as it's trying to interact and finding that the real world doesn't behave exactly how it planned, how it reacts to that context being clearly managed in a scratchpad is scratchpad prompting. So some of these things are just techniques that we start to introduce, and we start to try and make the models perform better using that as our optimization function instead of the next token prediction for text. So why are we learning about all this? Well, it's to get more out of your task and more out of more out of your model working on your code base. Often writing a tool to understand that code base or to be able to execute or like work on that code base becomes helpful. So what is MCP or what is tool use? So Anthropic came up with, or at least major contributor to Model Context Protocol, which is just has like very simplistically 3 stages. You have the reasoning model, you have a client, and you have a server. MCP allows you to discover what tools exist. So the tool server will tell the client all the different types of tools it has access to. It could be kind of file navigation or code authoring, running, building things, etc. Once the tools have been discovered, the reasoning model can ask for specific tools to be invoked. And MCP allows you to define the almost like a JSON format in which you can invoke the tool and the results that would come back as a response. The more I look at these things, the more I feel like we are reinventing the protocols of the past, but that's what MCP is, how a reasoning model should talk to a tool server. I'll give you an example in a moment, which will make this clear. But what are the kinds of tools? As I said, file discovery, compilation, version control, all that kind of good stuff. So once we have tool use, just as an example, like Copilot has all of these different tools. So if you are compiling tools, LinkedIn tools, build tools, etc. And then let's talk quickly about reflection, and then we'll go to multi-agent architecture. So reflection is basically the ability to reason about the work that you've done. And the couple of papers that I linked, I don't think I have time enough to cover everything in detail here. But these papers go through like the evolution of the techniques. But effectively, these techniques are hardening the ability of the LLM to be able to get the results of things like tool calls or the execution of its plans and be able to reason about it. So if I write some code, it comes back via the tool call. Like when I try to build it, or I invoke a build call, a tool call for building, the results of the build come back with a bunch of errors. Now I need to be able to reason about why those failed and try to fix them. And that becomes my reflection. So I need to start being able to reflect about the work I'm trying to do. Some people have called this like the rubber duck ability. So the ability for the model to talk to itself, or talk to a rubber duck to be able to figure out why things are failing and trying to debug it. So I think these are like the key core capabilities we discover. So we have tool calling, reflection. We haven't spoken a lot about memory, which we'll come to in a moment, and the ability to plan. So multi-agent architectures. There are a few different patterns here. So these patterns will get interesting. I'll go over them one by one. The most closest to what I can see value in for my work today itself is the product development lifecycle. So being able to analyze data, come up with an opportunity for something that we should be building as a feature, coming up with a product spec. So what type of product we should build, or what type of product feature we should build, coding that, testing it, setting up, especially in Meta, we do that a lot, setting up a public test where some set of the users get a new treatment, some are control, to be able to figure out if it's worth it to roll it out to the kind of few billion users that we will have eventually get access to it, and then the data analysis aspect to it. For each stage of this, the agents are optimized, and we have many of these components at various levels of maturity already. The ability to be able to do data analysis to find an interesting opportunity, translating that into a requirement spec, coding, testing, etc. Now this is a very sequential pipeline with a few feedback loops. It requires a communication protocol between each agent. And for the most part, much of this is actually still being doing via memory, which is writing down. When we say memory in this domain, we are basically writing an artifact down as a file or as a message, and we pass it to the right agent. And that's how we communicate back and forth. So this is a pipeline-based pattern. There are also hierarchical patterns where you may have a navigator driver style pattern where the navigator is trying to figure out strategically what needs to get done, and the driver is actually doing and executing on individual tasks. So by doing this, you can have the navigator focus on the big picture and the driver focus on getting subtasks done. And you can take this ad nauseam into a whole hierarchy. This is also common in coder and deep researcher kind of paradigm where you ask a coding agent to go out and, in our case, in Meta's case, it could be, I want to see a new type of reaction button on posts. And that's the prompt I give to the coder. Now the coder needs to figure out, what am I talking about? What is a post? What's a like? Where is the code base for it? So it needs to go in and look through a lot of internal documentation. So it'll pass that task on finding out what's with specific questions to a deep research agent that's going to go and search through our documentation and all the different project documents, etc., and find out enough context for the coding agent to figure out, okay, this is what we're talking about. Then the coding agent is going to go and navigate the file system for our code base to find the right files, and this goes back and forth between them. So yeah, but the usual way to look at this is one agent focusing on the big picture, one is focusing on specific subtasks. And finally, you can also have what's being called in literature self-negotiation. This is basically, you can think of as either collaborative or adversarial pattern. So one agent would write the code, one agent would do code reviews or create tests. Their objectives are different. The coding agent is perhaps trying to pass its work without any bugs, and the job of the code reviewer is to find faults, find issues. So each are optimizing for different functions, and they are working together in tandem, and the work flows back and forth between them, and that way they can be optimized and fine-tuned for the individual tasks or optimization function that they're focusing on. So I think this is the last slide on agent internals. context management. So I'm not going to go, I don't have time to go too much in detail here. We are still at the stage of doing message passing and kind of blackboard style models of communicating between agents. Effectively, we are rediscovering distributed systems here in this domain of how agents should talk to each other. So a lot of the things that currently models are tuned for are basically message passing and kind of sharing or moving on to like things like sharing an instruction register versus data storage. So we are just rediscovering a bunch of things. I think this will take a while to settle down, but all I can share at this point is that, yes, the way we talk between agents today is still by file sharing, writing our context down, passing instructions down either as a file or as a message queue. Yeah. Any questions so far?
So in that previous slide that you had there, where you were talking about like how the LLMs are communicating with each other, are they still communicating with each other in like human language, or is there more of a role for like vector database and like using like those things together?
Yeah. So the attempt in many cases is to keep agents as generic as possible. So that mostly because we are trying to not over-optimize and keep, because the model technology is moving so quickly, every time you try to make it very specific to your domain, you're starting to run out of like being the current latest. So natural language still seems to be winning out because you can slot, and we're also finding that different models do well at different tasks. So we haven't quite come up with a protocol of like language or like communication representation that they'll be good at, but I think eventually we will get there. Perhaps agents will also negotiate between them what protocol they want, which I haven't seen emerge, but I don't want to speak, like, I don't know if I can share many things, but these are things you will start to see. Yeah.
Yeah, similar question. Like you had made a distinction between sort of like traditional LLMs and those that are in agentic workflows, but the agent itself has an LLM or is using one. So how do you think about the decision of like what model is in each agent in your workflows?
Yeah, I think you have to, I'll talk about it in a moment, but I think you will want to have evals and benchmarks of what good looks like for your outcomes. Okay. That will help you select, yeah.
Sorry to cut you off. Just one follow-up. I don't know if you saw like last year around February or so, there was a CUDA engineer that CppCon AI announced, and they said, oh, this agent is really good at CUDA. We don't have to learn CUDA anymore, and they rolled it back about a month later. Since hasn't come up again, and it turned out the agent was overfitting, like kind of manipulating how it was solving certain solutions to meet the benchmark of tests to make it look like it was overperforming. So, you know, in an agentic workflow where you're evaluating like compiler errors, do you worry about agents essentially overfitting to those specific errors at that time in the workflows?
Yeah, I think I can, if I can summarize that question. So I'm not familiar with the CUDA engineer model. I can look into that. But just to generalize the question, it's about how do we ensure that models don't overfit to benchmarks? Quick answer to that is that we are already overfitting to benchmarks. Unfortunately, that is the reality. There is work that all the labs are trying to do, which is to try to not just benchmark hack, but they know that once they release a model, they will have to show performance against the benchmarks. So there's a little bit of reward hacking in every iteration. I think as a practitioner, if I'm not a model developer, if I'm a practitioner, what I would want to do is to define, like I was saying, and I'll come to it, but I'm not getting into it in detail, so I'll maybe speak about it right now itself, is to establish your own benchmarks for your own workflow. And I'll talk about how we can scale it up, but let's say we can define this is what, for this task and these actions, this is what a good outcome looks like for me if I can define that. And if I have like statistically large enough samples, then I can just start to like lift and shift these models as they evolve and be able to say which ones are good for which part of my workflow. I think what we see, at least if I can step out of like the software engineering domain and just look at like AI-based products for like consumer use cases, the way we've seen this evolve is each model has its own weaknesses. And often you might have to bifurcate like flow based on what you're trying to do and what the intent of the prompt is and what the intent of the domain is and so on and so forth. There is no king model yet in this. Not sure I've seen it yet. Yeah. Any other questions? Cool. Just moving on. We are almost at the last 15-minute mark, so I might have to speed up a little bit. So this section is just talking about how do we get more out of our interaction with the agents. So if you are in the second meme where you feel like, or the first meme which is like, it's just taking me longer to debug this thing, like it's not really getting me. The first thing I would say is like establish evals and benchmarks. So I think, yeah, let's talk about challenges first. So challenges are that you have to establish evals and benchmarks for what good looks like for you. If you are essentially zero-shotting your way into using agents, you will get some initial traction, but then you will be stuck in that the bottom of the slide, which is like you're still debugging the hard parts, which you did not realize you want to get. Also, what I think the previous person who was asking the question was also referring to, I think there is a lot of domain-specific knowledge for every code base. There are conventions in every code base. There are potentially like domain-specific languages in there. There's stuff that only you and your organization understand, which a zero-shot learner can only get this far with. So you will have to get, that's a challenge, and I'll talk about how we fix it. Let me not get into fixing part yet. There is still like finite amount of context that models can hold. Even with the latest like context windows, there's only this much you can hold, and there's take token cost to build up the context. So how do we manage cost and how do we manage the limits on sizes? And many things that work on like reasonably sized code bases don't work on very large code bases. So if you have like millions or hundreds of millions, tens of millions of lines of code, some of these things don't actually start to degrade quite quickly. So I think if you take only one thing from my talk, this is it. Evals and benchmarks. Defining cases which are like good and bad modes for your business, whatever you're trying to achieve, is critical. And I think you can start with manual curation. So like just having engineers familiar with that domain and that particular task, get human beings to do that task, and then use that as the basic corpus of like defining what good or bad will look like. Also often tracking like implicit signals. So in the coding example, if a human engineer starts prompts and has a session with the agent, but comes out of that not getting the task done, that is an implicit signal of like a thumbs up or a thumbs down. So you can use that. The key is like having diversity in the domain, language, difficulty, complexity of the code base. So like having enough variety of cases as well. So let's take a couple of examples here. So there's a Google paper I link. They started off with like just starting with 100 manually curated review comment patches. Like, so basically you have a code change and you have a bunch of reviews from human beings on that. And they just manually created 100 of these. And that was enough to get their SFT going. So like as a supervised fine-tuning for the off-the-shelf model, they were able to use that, and they talk about how they got value from that. So I think manual, almost like necessary to get a basic core corpus, but you can also automate, right? So you can pull up, most of us have tens of thousands of maybe that many diff comments, mine those out and be able to tell whether it's a good quality or a bad quality comment. If you're able to somewhat automate that, you're starting to get valuable like signals on what a good comment or a bad comment looks like, or which diff is a good one or a bad one. Why is it necessary? Because open source benchmarks don't capture that, which is what I think somebody was referring to. It will not capture like the patterns and the depth of your code base and the scale of your code base. So I think some of these things you need. So let's go deeper in this case study. So second paper there is from Meta, where what we've done is use both human and AI labeling. So this is like 3 stages here. The first stage was to get human labelers to go through diff comments, about 18,000 diff comments, like 7 annotators working for 14 weeks, like contractual workers working through that and labeling that. So that's your basic manual code corpus of 18 samples. Great, this is good to get bootstrapped. Now you start to build a small classifier. So take a small model like a Llama 8B model, and use some of those samples. At least if you come up with heuristic filters on those things that have been annotated, in this case, they took it down to about 7,500 samples, and they predict whether these are good or bad. So they're training a Llama 8B model to start predicting. And on a holdout about 700 other samples, they're able to kind of establish close to about 80% accuracy and like about 0.88 precision and 0.75 recall. So they now have one simple small model, a small classifier, and then they want to scale this up to about 46,000 samples. So like take a larger model and do a larger scale SFT on it, which is just to use these this level of classifier to train the larger model. Don't think I have enough time to go in through like why they did this and why this works. The paper talks about it, but effectively what it's saying is you can start to use off-the-shelf open source models, but start to fine-tune it for your domain and start to get value, and then you can do an eval between the one you fine-tune versus one you get off the shelf and see which one is performing well or not. Now, how do we deal with domain-specific knowledge? I'm going to have to go a little bit faster. So you're going to have to write MCP tool calls for some of these cases. But often what you will see is that the first few times you are using a model on the code base, you'll have to give the model a lot of feedback. And over that session, it eventually figures out what you're talking about and eventually got it to be right. What you can do at that stage is actually ask it to create a runbook for itself, which could be a natural language runbook of like what it has understood. Sadly, I'm not able to share that for a session from like Meta's internal tooling with you all, but if you try it with like something that's available off the shelf like Claude Code, you should be able to find. Essentially walk through a session to get to a point where you find that the model got it, get it to output its understanding of the code base or the task or the domain, and then use that as the input for the next time you use the same model or like same agent or some other agent. Why should we write MCP tools? So going back to the other slide about MCP, so you can write MCP tools to better understand your code base. Here I'm taking a very like a generic example where certain code bases will have dead code recycling technology, like basically you functions that have not been called for a long time, you can point a scavenger on it, which will basically add a macro to log a line every time that function is called on production, or sample it across like 100,000 calls or whatever. And if there are no new samples for 45 days or like a month, it's going to recycle that particular code. This is a pattern that exists in some code bases. Now, when I have an AI agent working on that code base, I might not want it to fiddle with the code that's going to be removed as dead code. Or maybe I want it to go ahead and remove the dead code. Depending on my needs, if I specify that in my prompt and the agent comes across this sort of annotation or macro, it doesn't know how to reason about it well, zero shot. So you can write a tool call which is of this nature, which would be essentially how to reason about, I don't know if you can see it here. Oops. Let me share that. Oops. Okay, I have lost that. I'm happy to show this after we finish our allocated last 5 minutes. Yeah, let me get this slide back up. Okay. Yeah, so you can write a custom tool, which I don't have enough time to show you, which are just small lambdas to be able to deal with better understanding or better dealing with your code base. Then there are issues on how large the context window can be. And here, the usual advice is to just ask the model to summarize and use things like session tracing and checkpointing. So if you're running out of context or if you feel like it's giving up, you ask it to take, most of these reasoning models have a trace that they log. You can ask it to checkpoint, and then if you run out of memory, you can ask it to go back to a good known checkpoint, which is this one. So you can ask it to hold checkpoints, And then finally, you can also manually define context about a particular directory or a particular code base for the LLM to be able to go and access. This is like the README files that you write for human beings. You can write similar ones for the LLM to reason about things as well. Finally, there is other more advanced techniques around like dealing with context window and memory better. Don't have time to get into details. I think the papers I referred to have much more on how at the model level they're dealing with it, but as a practitioner, how you can leverage those as well. And for reducing cost, a lot of the things that I mentioned for managing memory and managing complexity kind of apply. So session checkpoints will help. Just reducing the complexity of the code base obviously will help. And wherever needed, if you can ask the LLM to create code to do it deterministically rather than trying to like use LLM to do the task, get a sub-task done by deterministic way so that you can save tokens and save cost. The last one is like 3 case studies. I think I'm over time. I don't know if I can, Chris, I can keep going or cut? I have to cut. No. Okay, keep going. We'll keep the questions at the end. So 3 quick case studies on improving code quality, experimentation, reliability. So at Meta, we defined a code quality score, which is measuring things like maintainability. You can think of them as like lint errors, but things that a traditional linter cannot find easily because it either spans lots of files or it requires like understanding the code case semantically rather than structurally. So that's where LLMs can help us because they can understand really what is being done in the code more than the structure. So the code quality score has a couple of innovations. One is defining or helping the organization or engineers define specifically what type of issue they care about. And now we are at about 500 different types of issues. They range from things as simple as like a variable in code that's unused, which in some scripting languages actually still end up using a lot of memory, all the way to the code is far too complex than it needs to be. And there's like some criteria to define that. So that's one innovation, just getting the organization to define these quality features. But then there's a 2-stage pipeline using 2 different Llama models. One is one which identifies whether the code base has a particular type of issue, and the other one that verifies that the code base has an issue. If both of these agree, then that becomes a signal for either a human engineer or an AI agent to go and fix it whenever it becomes a priority because there are scores associated with it. And this is now being used by at the time of the paper's writing, 5,000 engineers, which has grown quite a bit. And it has about 60% like favorability feedback rate, which I think in some ways this probably means there's a work in progress. So yeah, either you can do it on an existing code base or you can do it on a diff. The issue collector kind of identifies the file, line, function, etc., and tags it with an issue and a score to it. And the validator is going to go in and confirm whether the score is good enough, or in some cases, it will give a score where the previous stage is not giving you a score, and these show up in the UI. Actually, they are not just showing up in the UI now. They are also used by agents as inputs to go out there and fix them. So a very quick example here. There are 2 files which have almost the same change in them in the same diff. So the issue is like maybe you want to go and deduplicate this logic that you're introducing. What we're doing here is, let's talk very quickly about the issue identifying or the issue collector agent. Both these models are Llama 3.170B models, and they've been supervised fine-tuned with our code base. So we'll talk very quickly about how the fine-tuning works, but just as a prompt, the prompt basically contains the kinds of issues we should see, not the entire exhaustive list, but it's enshorting the kinds of problems we wanted to see. So then because of the supervised fine-tuning on large number of samples, the AI is going to go and find new types of problems. And the output is kind of mentioned to be in this particular format. And the validator stage is basically validates each score. I'm actually probably skipping the details of the fine-tuning list, but those interested, please go and read the paper. It's pretty interesting. Again, here, this one is just going to go in and try to like antagonistically fight back to the issue. So its job is to be very sure that the issue was valid. Do I have time to? No, I don't have time to do the training, so I'm going to quick skip over, but that's a cool piece. The last two case studies are one on the diff risk score, which is like every time there's a diff, the tooling will give you a score on the likelihood of it causing an outage in the future. And here the paper talks about like 4 different models and approaches to do this. Encourage you all to read it. Finally, this is my paper, which is talking about test generation using LLMs and AI agents. This is a very simple system where you basically are looking at every diff and figuring out what it's changing and prompting a bunch of different LLMs to kind of agree on what test needs to be created. And if more than one type of agent agree, then the test is proposed as a candidate, which goes off as a diff, which human reviewers have to approve. And we have about 73% of those diffs getting approved by engineers. And it actually ends up, this agent is actually sixth highest in terms of diff created in the organization for a few months. That's it. All right, yeah, that's all I have. I'll stick around for questions.